Hi friend, you are welcome back to this channel, and in today's video lesson we shall be learning about another important and interesting topic in physics, which is rotational motion. So without wasting your time, we'll be starting now. Now for rotational motion, there are some key things you need to know. Rotational motion has to deal with the motion of a rigid body about an axis under the influence of force. So you see a body like this, okay, let's say this marker for instance, then it's turning about an axis. This is the axis, okay? It's turning about the axis under the influence of what? An applied force. It won't just turn on its own until a force is applied, okay, such that the body will rotate about an axis. That is the concept of what? Rotational motion. So what are the key things you need to know? Because this is the revision class, so I'll be giving you the straight important points you need to know for this topic, okay? Now the formulas you need to know will be given. But before we do that, let's look at this diagram here. This is a circular path showing the direction of a rotating body. So we are viewing this side, okay? As the body is rotating, we are trying to view this side of the rotation. And this is what we are. So the body is actually moving like this. Now, at the center, we'll call it the axis of rotation. So if you check, at every time interval this body rotates, an angle is being covered, an angle is being displaced, okay? Now that angle that is covered in every time is represented by theta, as you can see here, okay? And for every distance that this body will cover in that time interval, it will be represented by x, while the angle will be represented by what? Theta. So let's say the time was t. The angle suspended in that time t will be theta, while the distance covered in that time will be x. And like we all know, from the center to the circumference, that distance is specially called what? Arrow. And what is arrow? Arrow is what? Radius. So these are the key quantities you need to know before we start looking at rotational motion. Theta is the angle, s is the linear displacement or the linear distance, arrow is the radius. Is that clear? Now there's a formula we can use because under rotational motion, the unit for angle, theta, that we make use of under rotational motion is strictly the radian. We don't use any other units. So if you are given in degree, you have to convert from degree to what? Radian. If you are given in revolution, okay, you have to convert from revolution to radian. So this is the relationship between radian, degree, and revolution. And what is it? 2 pi radian is equals 360 degree, and that is equals to 1 revolution. So guys, now we have this at the back of our mind. We cannot get to see what are the formulas to keep in mind under rotational motion. So let's see them now. Now the first one is called angular displacement. Angular displacement is simply the angle at the center, the one that is being suspended, okay, during the course of the rotation. Now it is given as theta, and the unit for angular displacement is radian. It's not degree, neither is it revolution. So when you are given degree, convert to radian before you start solving or working with it. Is that clear? Now to get your radian, perhaps it wasn't given. To get your angular displacement, if it wasn't given, the formula is theta equals x over r. X here is the linear distance over r, which is the what? The radius. Now this is the formula that will give you your theta. Now what else? If you are asked to find what they call angular velocity, sometimes it can also be called angular speed. And the symbol for it in this case is omega. Omega, the W sign. Now the unit for angular velocity is radian per second. Just take note of all these important facts. Now what is the formula you use if perhaps you may not do the angular velocity directly? The formula to use is omega equals theta over t. Now the omega here stands for the angular velocity, or you say the angular speed, and the theta here is equals what? Angular displacement, everything over time. Now if perhaps you were asked to find angular acceleration, mind you this is different from the normal linear acceleration. So we'll be applying a different formula to get our angular acceleration. Angular acceleration is symbolized by alpha, as you can see here, and the unit is what? Radian per second squared. Observe the difference. While for angular velocity it's just radian per second, for angular acceleration it's radian per second squared. So there are difference between the two units. Now looking at it from here, what is the formula to get our angular acceleration? We can use alpha is equals to delta w or delta omega over t. I will explain. Alpha here stands for what? The angular acceleration is equals to delta omega. Now delta means change in. Okay, when it comes before a quantity, it's symbolizing change in that quantity. So delta w here talking about change in the angular velocity, because omega is angular velocity. So change in angular velocity, everything over time. Now when something changes, it means there was an initial of that stuff and there's a final of it, is it not? So we can further expand this delta w equals to be equals to w2 minus w sub 1, everything over t. So if you are given the change in the angular velocity directly, let's say they said the change in the angular velocity during the course of a rotation is, let's say, 20 radian per second in so and so time. Find the angular acceleration. You are given the change in angular velocity directly, so you just simply impute it and solve. But if you are just given two separate values for the angular velocity, a final value and an initial value, you have to make use of this formula. So straight to this place, we are going to be looking at what is called equation of rotational motion. Remember, at the beginning of the foundational level of physics, we were taught something called what? Equation of linear motion, or better still, equation of uniformly accelerated motion. But in this place, we'll be looking at the counterpart, the direct analog of that same thing, but in this case under rotational motion. So if the body was moving under uniform speed, now we know that if the speed is uniform, it means that there is no acceleration. So that's why the speed is being uniform. So if that is the case, for a uniform speed scenario or a zero acceleration scenario, these are the formulas you make use of. So they said a body is rotating under uniform speed, or a body is rotating under zero acceleration. These formulas should be what should come to your mind, because these are the ones that are going to be relevant. Now the first formula is theta equals Wt. Theta is angular displacement. It will be equals to what? Angular velocity times the time. But if you're given two values for the angular velocities, what do you make use of? Is this second formula. To get to angular displacement, you now make use of W1 plus W2 divided by time, divided by 2, everything times time. Now what you're actually succeeding in doing here is taking the average of the two angular velocity. You are taking the average of them, then you now multiply with what? The time. So if you're just giving one angular velocity, make use of this. But if you're giving two angular velocity, make use of this. Now moving on from there, what if the rotation was under uniform acceleration? That is the value for an acceleration in this what case. Remember, in this previous case, there was no value for the acceleration, so we say zero acceleration. But in this case, there is an acceleration. So what are the formula that we apply? Because there is uniform acceleration, these are the formula that we can use. We have W2 equals W1 plus alpha t. Now this is similar to the equation we have, the equation 1 under uniformly accelerated motion, which is final velocity equals initial velocity plus linear acceleration times time. But this is the direct analog of it in rotational motion. W2 here stands for what? Final angular velocity. W1, initial angular velocity. Alpha, angular acceleration. T, time. So it's just the same direct analog. Now moving on to this, you have theta equals W1t plus 1 over 2 alpha t squared. Theta here stands for what? Angular displacement. But in linear motion, what should be here would have been what? X, which is linear displacement. Is it not? But here it will be what? Theta. It will be equal to W1t plus 1 over 2 alpha t squared. This is the second equation of rotational motion. Now the third equation of rotational motion will now be W2 squared equals W1 squared plus 2 alpha theta. So take note of this formula. There are some questions you'll be given under rotational motion that will simply require you make use of them. So keep them at the back of your mind. Now there is a last scenario which is called motion or rotational motion under instantaneous acceleration. So far so well, observe the difference. In the first scenario, there is no acceleration given. In the second scenario, there is an acceleration. Now in the last scenario, the acceleration is changing with time. The acceleration in this third scenario is changing with time. So it is called instantaneous acceleration. The acceleration at a given instant in time, because it's going to change by the next time. I hope that is clear. So if that is the scenario, you can't make use of these formulas. There are a different breed of formula to use. The first one, if you have to ask to find the angular velocity. The first formula to make use of is the theta over dt. This is where differentiation comes in place. Okay, you have to differentiate the function that was given for the angular displacement to get your angular velocity function. Impute the value of time, you will get your answer. It's the same scenario because there's a direct analog of this in uniformly accelerated motion. So I'm just giving you the direct analog under rotational motion. It's the same thing. Now observe, if you were asked to find the angular acceleration and you were given a function for the angular velocity, differentiate the angular velocity, get the function for the angular acceleration, impute the value of time, you will get your answer for alpha. But if you're given a function for the angular displacement, you are going to differentiate the angular displacement function twice. That's why you are saying raised to power 2, raised to power 2. Once you have differentiated it twice, impute the value of time, you also get your alpha. So these are the key formulas we should have at the back of our mind. For what? Rotational motion. Now back now, we are not yet done. We'll be moving on to another aspect of rotational motion that has to do with what is called the moment of inertia. The moment of inertia. So without wasting your time, let's look at moment of inertia. Alright guys, about now we shall be learning about moment of inertia. Thereafter we shall be looking at radius of gyration, and then we'll be looking at torque, and then we'll be looking at angular momentum. And lastly, laws of conservation of angular momentum. So let's quickly get started with moment of inertia. Now first thing first, the symbol for moment of inertia is capital I. Moment of inertia is symbolized by capital I. And the unit for it, so when you have finished solving, the unit you should always attach is kilogram meter squared. Okay, that's the unit for it. Now what is the formula for moment of inertia? It is summation mr squared. But in most cases, especially at the O-level that you are, especially for O-level students, you can simply say I is equals to mr squared. Okay, they won't bore you with much complex case for moment of inertia. So what am I trying to say? You can just take it that moment of inertia is equals to mass times radius squared. Okay? It's only in complex cases in the advanced level that you need this sigma here. I hope that is clear. So moving on, there are some things upon which moment of inertia depends on. Moment of inertia, one, it depends on the axis of rotation. Okay? It depends on where the point of rotation is. Secondly, it depends on the shape of the body. Is the body rectangular? Is it cylindrical? And all that. Then lastly, it depends on the distribution of masses. How the masses are distributed in the body also affects the value for what? The moment of inertia. Now, we will be talking about radius of gyration. It is symbolized by capital K. And what is the formula for finding the radius of gyration? If you were ever asked at O level that you are. It is the square root of the value of the moment of inertia over the value for your mass. So radius of gyration is equals to root moment of inertia over mass. This is the formula to make use of. And then we're talking about torque. Now torque is similar to the normal scenario. Okay, let's just say torque in rotational motion is all about toppling over. Okay, a body is like this. Remember when I was defining moment in rotational motion, I said it applies to rigid body. So a body could have a body like this, and then when the body experiences a torque, it moves like this. So that toppling over is what is called torque. Okay, toppling over is called torque in rotational motion, and the symbol for it is this form of T, T that is utilized, and the unit for it is Newton meter. Newton meter. So when you finish finding the value for torque, always attach Newton meter as the unit. Now there are formulas, many formulas you can use to find your torque, depending on the variables that are given in the question. If you are given force and you know the radius in the question, you can simply use torque is equals to force times radius. Is that clear? Now if you are given the mass of the body and you know the acceleration, in this case linear acceleration, mind you, this form of A, the normal A we know, stands for linear acceleration. Okay, it stands for linear acceleration. But this form of A, which is called alpha, stands for angular acceleration. So I'm trying to say here that if you know the linear acceleration, not the angular acceleration, you can use this formula, mass times linear acceleration times radius. Now if perhaps you now know the angular acceleration, not the linear acceleration, the formula to use to get your torque is mass times radius squared times angular acceleration. Now lastly, if you were given the moment of inertia, which is I, if you know the moment of inertia, you can simply use torque is equals to moment of inertia times angular acceleration. So that is all about torque, okay? Now we'll be talking about angular momentum because everything is under rotational motion. Now, angular momentum, the first thing to know is that the symbol for angular momentum is capital L, okay? And the unit for it, so we are done finding your angular momentum, the unit you should attach to it is joule second. Joule second is different from that of torque, which is Newton meter. I hope that is clear. Now, what are the formulas you can use to get your what? Angular momentum. The first formula, okay, which is the formula in the vector form, is angular momentum is equals to linear momentum times r. So take note, this form of P that looks like it's slanting is equals to linear momentum. I hope that is clear. Okay, linear momentum. But this form of L that is slanting is what we now call angular momentum. So I hope all these are being taken note of. I hope they are being taken note of. Now, if perhaps we are given the linear velocity, not the angular velocity, you are given the linear velocity, not the angular velocity, the formula to use is angular momentum is equals to mass times linear velocity times radius. If you are not given the angular velocity and not the linear velocity, this is the formula you use. It will now be equals to mass times radius squared times angular velocity. Now if you know the moment of inertia and you are asked to find angular momentum, the formula you simply use is moment of inertia times angular velocity. But if you are asked to find torque, it will be moment of inertia times angular acceleration. I hope this is clear, guys. Then under this, we'll be looking lastly at the law of conservation of angular, not linear momentum, angular momentum. Now, from what the law states, it says that if there is no change in the torque that is acting on the body, the angular momentum will remain constant. That is just a paraphrased form of it. And the formula we're able to mathematically deduct from that statement is what is given here. It is moment of inertia 2 times angular velocity 2 is equals to moment of inertia 1 times angular velocity 1. That is to say, the angular momentum, because we know that whenever we times moment of inertia and angular velocity, we get angular momentum. So the angular momentum after is equals to the angular momentum before. It shows that what there is conservation of angular momentum. So this is what we are talking about. So lastly, under rotational motion, guys, we'll be talking about rotational work, energy, and power. So let's get on to that now. So guys, in this very aspect, we'll be talking about rotational work, rotational energy, and rotational power. So let's get started. Rotational work. For rotational work, the unit for rotational work is still the same unit for normal work, which is joule. Now, the formula to make use of when you are asked to find the rotational work done is torque times angular displacement. Remember, for normal work done, we say force times displacement. But because this is rotational motion, instead of force, we will say torque. Now, instead of distance, we will say what? Angular displacement, which is theta. So observe that similarities. Now, for rotational kinetic energy, or just simply rotational energy. Now, why do I have to be specific here? There is nothing like rotational potential energy, because a rotating body is already in motion, and the energy a body possesses when it is in motion is only what? Kinetic energy. There is no potential energy under that scenario. So that they can just say calculate the rotational kinetic energy or calculate the rotational energy. It's the same thing they are talking about, and the units remain joule. Now, the formulas you can use depending on the variables given is energy is equals to half moment of inertia times angular velocity squared. Now, this is similar to the normal formula for kinetic energy, as we all know. Half mv squared. That is to say, moment of inertia is similar to normal mass, and angular velocity is similar to linear velocity. So they are just analogous to each other. Now, from here, if I expand this, I have 2W. If I attach 1W to this moment of inertia, I times W. Remember, what does that bring to your mind? What does that make you remember? I times W give you what? Angular momentum. But there's still an extra W. So this will give us another formula. Energy or rotational energy is equals to half angular momentum times angular velocity. So this is the next formula. And lastly, we can also get, if you convert this, okay, if you what I call it now, if you express this further, remember W here stands for angular velocity and I here stands for what? Moment of inertia. If you express this in terms of angular momentum, if you express moment of inertia in terms of angular momentum, you will get this, okay? L squared over 2I, okay? This is what we will get. If you express angular velocity in terms of I, you will get this. So what's the last formula? Energy is equals to angular momentum squared over 2 times moment of inertia. So these are the three basic and important formula for rotational energy, or you say rotational kinetic energy. Okay? Now let's talk about rotational power. For rotational power, there are three important formulas. If by chance you already know the rotational work done, simply divide it by the time given, you will get the rotational power. And the unit is same as that for normal power, which is what? Watts. Now, if by chance you already know the rotational energy or rotational kinetic energy, divided by the time, you will get the rotational power. But if you are given the torque and the angular velocity, to get the rotational power, the formula to use is rotational power is equals to torque times angular velocity, and this will give you the rotational power. And the unit should be what? Watt. So I clearly hope you understand all this that was said under rotational work, energy, and power. Thanks for watching this series on rotational motion. Do it to try and answer some questions relating to this topic. See you in my next video.